Hello, everyone. Today we are together with Sayak. Hi, Sayak. How are you?
Yeah, I'm doing good. How are you, Janet?
I'm good. I'm good too. Thank you. So I think we can start. That's okay.
We could start, but would you like to wait for 1 or 2 minutes for other folks to join in?
Sure. Of course.
What would you suggest, Janet? Should we get started?
Yes, if you're ready.
Yeah, I'm ready. Couldn't be
Okay.
more ready.
Okay.
Yeah, cool, cool. Hello, everyone. Thanks for joining today's session. My name is Sayak. I'm a deep learning associate at Pioneer Search. I work at the intersection of computer vision and deep learning, and I'm also an active contributor to TensorFlow Hub. I really like to work with TensorFlow Lite, specifically in the area of model optimization. And today I would like to talk to you about a few good stuff in TensorFlow Lite. And if you are wondering, then the title of this session is taken from the movie called A Few Good Men. I'm not sure if you have watched that one, but it's a pretty good one. So yeah, you might wanna see it in your leisure. Specifically, we are gonna be covering a number of different non-trivial scenarios that might be highly relevant and practical when you are working with TensorFlow Lite. So without any further ado, as they say it, let's get started. And first things first, if you have any questions regarding any of the things that we are going to be discussing during the session, or any questions in general, deep learning or machine learning, please feel free to ask them right away in the comment section. I'll be checking them in between regular intervals. So I'll try to, have your questions answered as quickly as possible. Or else you can wait till the session finishes, and then if time permits we could do a formal Q&A. So all good, I hope, and let's actually get started. uh, so the ideal audience for this session would be developers that have worked on image-based models, specifically in Keras. It's not like if you have worked on NLP and things like that, this session won't be useful for you. But the things that I'm going to be presenting would be more in the line of image-based models and stuff like that, because I find it easy to demonstrate these kind of things with image-based models. So that's the rationale behind that. and this session is going to be highly helpful for the engineers that are looking for ways to optimize models for deployment purposes. Because at the end of the day, you would want to have highly optimized models that are performant, and at the same time they are capable of producing accelerated inference, right? Naturally, it would be cheaper to host a 10 MB model than it would be to host a GBF model probably. So anyway, you would want to optimize your model when it comes to real world practical scenarios. So what's the motivation behind putting together this deck in the first place? So today's presentation, or let's just say discussion, would be resolving around these four things primarily. The first would be, I often say, many of the state of the art machine learning models are still in TensorFlow 1.x. So how do I convert them using TensorFlow Lite V2 converters? Are they even compatible in the first place? The second thing I often get asked is, not all the operations can run on TensorFlow Lite GPU delegates. And this point is particularly very important if you are planning on deploying your TensorFlow Lite model on mobile applications, and at the same time, if you are planning on using TensorFlow Lite GPU delegates and stuff like that. Third thing is, as you may already know, that post-training quantization results in lower accurate models, right? It often changes the performance nature of your original model. So how to deal with those scenarios, right? And last and probably one of the most obvious things, how could I take advantage of TensorFlow Lite APIs when my model is not in non-TensorFlow format? Because at the end of the day, if you are using other frameworks like PyTorch, and if you still want to take advantage of TensorFlow Lite based APIs, is there any systematic way to do that? So as I mentioned, I get asked about these questions quite a lot, and I hope you have also asked yourselves these questions and you have faced issues similar to this. So no worries, in this session forward, we'll be discussing all of this stuff and how to approach them in a systematic way. So hopefully this is going to be useful for your own projects as well. So first thing, TensorFlow Lite V2 converter for TensorFlow 1 models, because as I mentioned, many of the state-of-the-art models that we see today are still in TensorFlow 1.x, right? First, let's tackle this question: why use the V2 converter in the first place? Because we already have a TensorFlow Lite converter in TensorFlow 1, right? So why the need? Because the TensorFlow Lite V2 converter is quite enhanced. It supports the latest MLIR support, which is Google's compiler infrastructure, specifically designed for handling high performance computing related stuff, which is very useful for machine learning related workloads. Second point is, TensorFlow Lite V2 converter comes with improved kernels, and that would naturally result in more performant TensorFlow Lite models, and the V2 converter also supports more operations so that you do not run into incompatibility errors and stuff like that. So I hope the need to use TensorFlow Lite V2 converter is clear up until at this point in time. So moving along, assuming your TensorFlow 1 model comes in checkpointed format, and the checkpoint format looks something like this. And here's the conversion workflow that we are going to be discussing. So first and foremost, we are assuming that the TensorFlow 1 model comes in checkpointed format. And I'm sure you are kind of familiar with these model formats that are very common in TensorFlow ecosystem, I would say. So the first and foremost thing you would want to do is instantiate your main model class and load the model checkpoints that we saw earlier, and then load all of those checkpoints in your model's current session, right? So you would first instantiate your model class, you would load your model checkpoints in the session that you use, right? And then you would connect your input and output tensors of your original model and export that particular session as a saved model format. And I'm sure saved model, you know by now, saved model is another model serialization format in TensorFlow. And I would say saved model is kind of the format that unifies the entire TensorFlow ecosystem because it communicates with the other TensorFlow related products, such as TensorFlow Core, of course, and TensorFlow J, for example, right? And TensorFlow Extended, of course. So after connecting your input and output tensors of your original model, you would ideally export the session to saved model format, right? And no worries, I'm going to be sharing all of this code with you. I'm going to be sharing the entire deck with you. So you can just focus on the things that we are discussing. And now you know the drill, because once you have a saved model exported with you, it doesn't matter in which TensorFlow runtime the saved model was exported in, right? It could be in TensorFlow 1.x runtime, it could be in TensorFlow 2.x runtime. If you have a saved model, then you are pretty much the halfway through, I would say. So after you are done exporting the saved model, you can switch to a TensorFlow 2 runtime, and you can use the TensorFlow Lite V2 converter, and you know the drill from here. You would typically use the from underscore saved underscore model function from the TF Lite converter, and yeah, you can play with all the other nifty options that come with TensorFlow Lite APIs while you are converting your TensorFlow Lite model. So yeah, I hope you know the drill from here. But my idea was to get you to this point, right? How should I proceed when I have checkpointed models in TensorFlow 1? So I hope you now have a systematic workflow. Looks like we have got a couple of questions. Let me check them out real quick. Oh no, hello guys. I hope you all are doing well. Oh, hi Boris. Boris is also in the session. Hi Boris. Nice to meet you again. Okay, cool. Let's proceed to the next thing. And it of course works, right? I mean, how useful it would be if it doesn't work, if the workflow doesn't work in real time, right? So it works. The workflow of course works. And here's the kind of output you would see given you are using the same model. So here I used the You Got It model. It's also known as the selfie to anime model. So yeah, we used that particular model to demonstrate this workflow, and this is a joint effort between Margaret, who is another machine learning GD, myself, and the other TensorFlow Lite team members. So I hope this workflow is going to be immensely useful for you too as well. So I have also linked the entire tutorial that would walk you through all the nitty-gritty details of this workflow. So I hope you would be able to follow along with them. And yeah, as always, if you have any questions around them, feel free to ask me away. So what if your model comes in a frozen graph format, right? We already know how to deal with model checkpoints. We know how to deal with saved model format. What if your model comes in frozen graph, which is pretty common in TensorFlow 1, right? In TensorFlow 2, there's no such thing called frozen graph. So even if your model comes in frozen graph format, you can still pretty much use the V1 side of things within the TensorFlow Lite, within the TensorFlow 2 runtime, and you can still, make use of all the features that you would get with TensorFlow Lite V2 converter. So here's how you would do it. You would simply use the from underscore frozen underscore graph function from the V1 TensorFlow Lite converter. So that's it. So the next thing is optimal performance on mobile. So TensorFlow Lite was kind of developed with one of the primary objectives of supporting mobile application developers who are looking into bringing machine learning powered intelligence in their applications. So what good it be if your TensorFlow Lite model does not run optimally on a mobile phone, right? And this section is going to be all about that. But before that, if you have any questions, feel free to ask away. Otherwise, we can proceed. Okay, looks like we do not have any questions, so we'll just proceed. So when you are, in that process, when you are in that zone of deciding whether or not your TensorFlow Lite model runs optimally on the mobile phones that you would deploy your mobile application to, the first and foremost thing you would want to do is benchmark your TensorFlow Lite model. So TensorFlow Lite provides this tool called TensorFlow Lite Benchmark, which allows you to, uh, benchmark the performance of that particular TensorFlow Lite model, and it also, provides you with a comprehensive list of all the operations that might not run on TensorFlow Lite GPU delegate. So if you were planning on using TensorFlow Lite GPU delegate within your mobile application, then this tool summary is going to be highly beneficial for you. No, okay. I guess I'm back. And if someone could confirm if my screen is visible and I'm audible, then it would be great. Just say yes or no if my screen is visible and if I'm audible at the same time. If someone could confirm via the comment, that would be great. Folks, am I audible and my is my screen visible? Sorry about the internet glitch. I'm really sorry about that. But now that I'm back, so yeah, I hope my screen is visible. Yeah, it is. Yeah, so we were discussing in order to make sure that your TensorFlow Lite model runs optimally on a mobile phone, you'd want to use the TensorFlow Lite GPU delegate in order to accelerate the inference. So you first want to run the model benchmark tool in order to know about the general performance statistics of your TensorFlow Lite model, and at the same time, what the benchmark tool would do is it would provide you with a list of operations that won't be supported by the TensorFlow Lite GPU delegate. So it's going to be highly useful. So here's how you would run a particular TensorFlow Lite model with the benchmark model tool. And this is the kind of output that you would get out of it. So as you can see, it's kind of very comprehensive. It provides with all the necessary statistics regarding model inference and similar things. It also shows you that the TensorFlow, the benchmark tool actually applied the GPU delegate. So all of the things regarding the inference statistics that you would see, you are sure that they are they were generated after running your TensorFlow model using the TensorFlow Lite GPU delegate. So that's one thing. Running your TensorFlow Lite model on the TF Lite GPU delegate is one thing. Benchmarking your TensorFlow Lite model is another thing. But here comes the most interesting bit, and believe me, this is going to be very interesting. So what should I do if I encounter some operations are not really supported on the TensorFlow Lite GPU delegate? Ideally, you would want to maximize the total number of operations in a TensorFlow Lite model that would be supported by the TensorFlow Lite GPU delegate. So after running your TensorFlow Lite model through the model benchmark tool, you would start inspecting your original model. So let's actually do this. Let's do this live, and let's use a tool called Netron. It's a very famous tool for inspecting different neural network models and stuff like that. So what I'm going to be doing, I'm going to be stop sharing this screen, and I'm going to be sharing to my other screen. Share screen, window. Wait. Okay, cool. The output is kind of inconvenient, I would say. So let's actually do this. So here I have already downloaded a particular model, and this is the deep lab model for doing image segmentation and stuff like that. This is just one particular variant of deep lab v3 model. There are many. So this is based on MobileNet v2 with a depth multiplier of 0.25. So this comes in both checkpointed format, and it's also accompanied by a frozen graph. So what I'm going to be doing is I'm going to be loading this frozen graph, and I'm going to be start inspecting it within Netron. So let's see. I'll give it some time to load. Okay, so this is the kind of interface that you would get in Netron. So let me just quickly make it full screen. And as you can see, this is the input tensor of the particular model that we are currently seeing. And here we can see that this particular model actually takes dynamic shaped input. And how would you know that? You could know that by seeing this kind of shape. If your shapes include question marks, then the model does not yet know what shape, in which shape your inputs are going to be appearing. So this is very important to make sure that the TensorFlow Lite model has fixed shaped inputs, because dynamic shaped inputs are not yet supported by TensorFlow Lite GPU delegate. So this is important to make sure that your TensorFlow Lite model only takes fixed shaped inputs. It's not that TensorFlow Lite models cannot handle dynamic shaped inputs with TensorFlow Lite 2.3 binary. It's possible, but TensorFlow Lite GPU delegate doesn't yet support that. So what I'm going to be doing is I'm going to be trying to find which particular tensor has fixed shape input. Let's see. So now I'm trying to traverse this entire graph, which is pretty messy. And let's see, I'm going to be traversing down. Okay. So we do not have any shapes here. We do not have any shapes here. Do we have any shapes? No, we don't have. Reshape, we still don't have. Yeah, so after this particular dynamic shape, we haven't yet got to any tensor which has fixed shaped inputs. So let's see. Yeah, in this particular tensor, as you can see, it has a fixed shaped input. As you can see, there are no question marks in there, and the shape is 1, 513, 513, 3. It means it's gonna take images having 3 channels, probably in RGB format, and the dimensions would be 513 and 513 respectively. So yeah, so what I'm going to be doing now is, so you saw that up until uh, up in this particular tensor, we got something that has fixed shaped input, right? Now we have already left behind all of this stuff. This is usually the pre-processing step that you often apply to your input data before feeding that to your particular model. So let's see where to go from here. So I'm going to be quickly swapping my screen here. I'm going to be quickly sharing it. Okay, we are good. Cool. Okay, cool. Now we are back. Okay, let's see. So where to go from here, right? We saw that how to extract a particular input tensor from the original model, which has a fixed shift input, and why would we want to, deal with TensorFlow Lite models that has fixed shift input? Well, that's because TensorFlow Lite GPU delegates won't support dynamic shift input as of now. Okay. So as I mentioned, what to look for? Does the model support dynamic shapes in the input? And also, does the pre and post processing subgraphs, as we saw, the original model graph included the several pre-processing steps, as we saw, are those operations supported on TensorFlow Lite GPU delegate? Because remember, we would want to maximize the number of operations that are supported by TensorFlow Lite GPU delegate, because in that way we would be able to make sure that we are getting accelerated inference out of our TensorFlow Lite model when they are being executed from mobile applications. Cool. As I mentioned, dynamic shapes are not supported by TensorFlow Lite GPU delegate, and operations like argmax are not supported by TensorFlow Lite GPU delegate. So these can lead to latency issues. So which is kind of problematic if we are dealing with mobile applications, right? We would want our mobile applications to be fast and performant. And imagine, while you are typing the next word that you are getting to see in your Gboard, that prediction is being delayed. You wouldn't certainly want that, right? So we saw that we got a particular input tensor which had fixed shapes. So now while converting my frozen graph, by now we already know how to deal with frozen graph in TensorFlow Lite 2. While converting my frozen graph, I'm going to be instructing the converter that, hey, the graph should start from that particular tensor which has fixed shift input. And how do I know about that? We just, walk through that process of finding a particular tensor from the original model graph that has fixed shift inputs, right? And similarly, the output arrays. You'd want to cut your TensorFlow Lite model graph up to that part where maximum number of operations are supported on the TensorFlow Lite GPU delegate. Cool. So after we have made sure this is the case, we are not dealing with dynamic shapes and similar things. We would want to also make sure that while feeding our inputs to our TensorFlow Lite model, our would-be TensorFlow Lite model, the input data is going through the same pre-processing, and the results of your TensorFlow Lite model are going through the same post-processing steps, because we did not include the pre and post-processing steps in the TensorFlow Lite model. So those steps are needed to be in sync with the original model graph, right? Cool. And this workflow, of course, works. And I actually, tried this workflow on the model that we just saw in Netron, which we investigated in Netron just a while back, and it perfectly works. And thanks to Khan from the TensorFlow Lite team, who helped me a lot in getting this workflow, up and running. So feel free to check out the link that I have included in the deck. So yeah, feel free to give it a try and let me know. If you have any questions, feel free to ask away. Otherwise, we can proceed to the next section. Which one you are referring to, Busra? Which slide you are referring to? If you could comment that, that would be great. Okay, I guess we can just proceed. I'll try to address if you had any questions later, towards the end of the session, of course. Okay, let's proceed. So let's understand that post-training quantization, all of the things, all of the conversion steps that we saw in the previous slides, they are all referred to as post-training quantization, right? And post-training quantization has its benefits, and at the same time it has its disadvantages, right? Because it can lead to less performance models, because ideally what you are doing is you are reducing the precision of your model, and the loss in precision, numerical precision, can lead to lesser performant models. Okay, cool. Cool, Busra. I hope your question was answered. So as I was mentioning, post-training quantization can lead to lesser performance models because of the numerical precision loss, and there might be situations where you wouldn't want any loss in model performance in the TensorFlow Lite model, right? So how to make sure that? Well, here's one approach. So mitigating the information loss of post-training quantization. Let's see how to do that. As I mentioned earlier, post-training quantization introduces information loss. In other way, it actually reduces the numerical precision, which can lead to drop in model performance, which is other way of saying that it can introduce information loss in your model, because ideally when you reduce the model precision, it leads to information loss, and this can indeed lead to drop in models accuracy and models performance, just to be very generic. Sorry. And enter quantization aware training. So ideally we would want to train our models in such a way that they learn to compensate for the information loss as if they were to get quantized, and in that way we should be able to retain the accuracy to a greater extent, right? So what if we could instruct our model in a way that it could automatically learn to compensate for the information loss that would get introduced if it was to get quantized, right? So it's also known as quantization aware training, and here's how to do it. Here's how you would define your Keras model using the sequential API. And this is just the one line of code that you would need in order to instruct that, hey, you should get trained using quantization aware training. And in this case, the entire model would get trained using the quantization aware training. But there are possibilities, and there are in fact, implementations and APIs that come with the TensorFlow model optimization toolkit that would allow you to only instruct that, hey, you should not get trained, the entire model should not get trained using the quantization aware training. Only parts or certain layers of your model should get trained using the quantization aware training. So that's absolutely doable in TensorFlow model optimization toolkit. So here we are instructing the entire model to get trained using the quantization aware training, right? And rest of the things are quite similar, right? You'd compile your model in the same way, you'd fit your model in the same way. And that's pretty much it. And here you can see the kind of performance benefits that you'd get out of quantization aware training. So for example, the first model was not trained using quantization aware training. And when I actually used post-training quantization to quantize the original model that was not trained using quantization aware training, it gave me an accuracy of 75.09%. And when the same model was trained using quantization aware training, it gave me an accuracy of 92.72. I mean, this model was, of course, quantized after it was trained using quantization aware training. So you can see the kind of increase and the kind of benefits that you would get out of quantization aware training, and the latency kind of things, they all remain the same if you incorporate quantization aware training. But so depending on the kind of applications that you are using, depending the kind of hardware you are using, you would want to mix and match between the different options that come with TensorFlow model optimization toolkit and TensorFlow Lite. So yeah, you might not be using an Android application to deploy your TensorFlow Lite model in the first place. So this chart would come real handy there. And I left you with a but. So let's start the section of but now. Quantization aware training can take substantially more time, as you can see. The first bar that you are seeing here denotes the model training time without quantization aware training, and second one denotes the model training time with quantization aware training. So you can see it's more than half, right? And you might want to, fully integer quantize your model using the TensorFlow Lite APIs. So during the time I was putting together this deck, enforcing the full intake quantization was not possible, but it's still work in progress, and you might want to follow this GitHub issue thread to know more about the hacks around that, because integer 8, the full integer 8 enforcement is kind of a requirement if you are deploying your TensorFlow Lite model to an HTTP USB accelerator. So yeah, please feel free to follow along this particular issue thread if you want to know about the hack around this problem. And quantization aware training requires the entire model to be written in Keras, and it also assumes that you have got full access to your model code and the training dataset. And these three things might not be the case, right? You might want to write your model in TensorFlow estimator. You might not have got access to the model code in the first place, and worse, you might not have the training dataset with you, right? You might be a part of a different team where your sole focus is to optimize your original model. So you might not have access to your training dataset. But quantization aware training requires you to have access to all of these three things, right? So if you do not have any of these three, you might not be able to use quantization aware training in the first place, right? So just keep this in mind. And it's important that you specify this optimization flag, and you would want to specify this particular optimization flag, because with TensorFlow Lite APIs, you get to choose between 3 different optimization flags, like optimize for size, optimize for latency, and the default one. And when dealing with models that were trained using quantization aware training, it's important to set the optimization flag to this one only. Otherwise, your model, can behave in unexpected ways. And that is because during quantization aware training, fake quantization ops that get inserted to the original model execution graph, they are in integer 8 precision. So that's why. And if your quantization aware training model fails to produce good performance after the post-training quantization step, report this phenomena immediately, because this was one of the primary objectives behind training your model using the QAT scheme. QAT stands for quantization aware training. That is to be able to retain the same kind of performance even after your model is quantized using the post training quantization APIs of TensorFlow Lite. If that's not the case, report that immediately, right? As you can see, folks have reported about this phenomenon in the past, and if you are encountering similar phenomena, feel free to report them on GitHub. Cool. So this brings us to our last section, where we are going to be dealing with the issue. We are going to be dealing with the question: how do I convert non-TensorFlow models in TensorFlow Lite, right? So here's the workflow to follow. ONNX should be your best friend here, and ONNX stands for Open Neural Network Exchange. It unifies the set of operators and the data types that are typically used in order to define neural network architecture, and it supports a number of different frameworks, including TensorFlow, PyTorch, and so on. So export your non-TensorFlow model in ONNX format first, and ONNX format is nothing but .ONNX, as simple as that. And then take that ONNX formatted model and convert that to TensorFlow using the ONNX TF library that's specifically for converting an ONNX model to TensorFlow. And you know the drill from here. The ONNX TF library would spit out a frozen graph for your TensorFlow for the ONNX model that you would convert. And once you have a frozen graph file of your TensorFlow model, you know the drill from here, right? We have discussed all of that. And I have also, linked to a notebook that demonstrates this workflow end to end. So feel free to check it out as well. And please be careful, because if you use select TFOps or flex TFOps, as they say, during TensorFlow Lite model conversion, then it's not usable in the TensorFlow Lite Python interpreter as of June 2020, at least using the TensorFlow 2.2.0 runtime, right? But if you can upgrade to TF nightly, then yeah, select TFOps and flex TFOps are supported in TensorFlow Lite Python interpreter. But if it's not possible, then this might be an issue for you. So the deck is available here. I hope Zenep will be able to pop this on the screen. Yeah, thank you. And yeah, that brings me to the end of this talk. And I would love to get connected with all of you. My Twitter is Rising Sayak, RISING SAYAK. I'd love to get connected with you all on Twitter. And if you have any questions, feel free to ask away. We have got plenty of time.
Hi. Thank you so much for your presentation.
Yeah, thank you. My pleasure. Yeah, so I'm open to questions and stuff. So if you have any questions around TensorFlow Lite, or if you have any questions around deep learning and machine learning in general, feel free to ask away. Now is your time. And if you don't feel comfortable asking it right away, please, feel free to use Twitter and ask me.
We will be saving this video, so you can always find the video in our channel.
You can wait for a couple of minutes to see if folks have any questions. After that, we can call it a day off. It looks like we do not have any questions. And yeah, as I mentioned, if you folks have any questions around TensorFlow Lite or machine learning and deep learning in general, feel free to use Twitter and ask me right away. So Zenep, I guess we can call it a day off now. And yeah,
Mhm.
it was a pleasure.
Yes, for me too. It was a pleasure. Thank you so much for coming.
Yeah, of course. Good.
So have
And
a
I
nice
hope
day.
to, yeah, you too.
Yes,
Bye. Thanks, everyone.
you were, you were saying something. Thanks everyone for coming. You can always find our videos in our channel and be sure to subscribe to